All right. Can everyone hear me okay? I mean, I know I'm American, but am I loud enough? So I'm actually kind of staggered at the turnout here. I'm like, I'm not saluting. I'm like looking over the crowd, blocking the lights. This is kind of a niche topic, and there is a lot of you in here. Usually when I give this talk, it's like 25 people show up, maybe 30. I'm like, that's really neat, but what am I ever going to use this for? You'll come up with something. So welcome, everyone. How you all doing today? Good? So welcome the few, the proud, well, actually the many, the brave, I made it to the last session at day one. Usually by the 5 o'clock session, I'm like, my brain's full. I don't want any more. Can I just have a beer, please? So, and I know that many of you are probably thinking that anyhow, and you chose to come. So I will not keep you here too long. I want to make sure you get your beer. So, yeah. Hooray for beer, yeah! Who doesn't like beer? My wife, actually, she doesn't like beer. She's more of a wine person. So, my name is Guy Royse. I'm a developer advocate at Redis. I like to joke that there's 3 things on the slide that matter, but there's actually really only 2. One of them matters to you. One of them matters to me. One of them matters to my boss. The thing that matters to my boss is, where's my pointer at? It's not there. Is that Redis logo right there? I'm a developer advocate, so I'm paid to come to these events. This is part of my job, and my boss wants you to know, and I kind of want you to know too, that Redis is more than just a cache. It does a lot of stuff, and we're going to look at some of the stuff Redis does today. This is not a talk about Redis. This is a talk about probabilistic data structures. Redis has some probabilistic data structures in it, so I'm going to talk about how several probabilistic data structures work. We'll do a little bit of a demo with Redis, but mostly we're going to talk about the probabilistic data structures. And so that Redis logo is there is important to my boss. The thing that's important to me are all those social media links on there. I judge my worth as a human being by the number of followers I can get on social media. You'll see I've got a Twitter account up there. I've been rethinking that lately. I don't know what else to replace it with yet, though. So I know a lot of people are moving to Mastodon, but I haven't figured out where I want to go on Mastodon yet. And the thing that matters to you is that GitHub URL. So I've got all these code examples. I've written several probabilistic data structures in all sorts of languages. And by all sorts, I mean JavaScript, Java, and C#. That's like country and Western music, both kinds. And the sample that I have where I'm going to analyze UFO sightings, the words used in UFO sightings, and that's written in Python. So all that code's out there. Lots of different languages. The language doesn't matter because it's really the pattern of the data structure that matters. So that GitHub URL is where all that stuff is at. And there'll be a QR code at the end that will also take you to the specific repository for this talk. Sound good? Excellent. So this is a big number, 112,092. It's actually kind of a surprisingly large number. This is the number of UFO sightings that the National UFO Research Center in the United States, for North America, or for the United States only, this is the number of UFO sightings they have in their database since 1950. It's quite a bit. I'm sure they're all real. But I was surprised at how large it was. It makes for great data to play with. And we're going to play with it some today. I'm going to use it in all my examples. The data itself comes from the NUFORC's website, the National UFO Research Center, NUFORC. And it's locked up on their web pages and stuff like that. But this enterprising young man named Timothy Renner, who I always give credit for this, he likes doing research with weird data science specifically. And so he has written code to screen scrape these websites. The NUFORC website is one. The Bigfoot Field Researchers Organization for Bigfoot sightings is another. He also, the Haunted Places Index of North America, screen scrape that. So he's got these CSV files that he does machine learning with, full of all this wonderful, ridiculous data. The Bigfoot one is really fun because he did clustering analysis to try and figure out where Bigfoot sightings tended to happen, like what was the pattern. And, so he uses a clustering algorithm to group those Bigfoot sightings and got these sort of arbitrary clusters in different areas. And he couldn't figure it out until he laid a vegetation map over it. And then he learned that you could find Bigfoot in the woods. He did a similar thing with the UFO data and discovered that some 80, 90% of UFO sightings are within 50 miles of a U.S. airbase. Shocking. The funniest one, I think, is the day, by an order of magnitude, that has more UFO sightings than any other day of the year in the United States is the 4th of July, Independence Day. By the way, New Year's Eve, number 2. Dad, is that a firework? No, son, that's a UFO. So there's 112,000 of these things. It's fantastic. And the data is a lot of fun. It's actually, in some ways, kind of remarkably plain for what it is, because it's just sort of the report. We've got, in our data set, we've got a summary of the UFO sighting. Here we've got 3 saucer-shaped ships, which is very hard to say. Sioux sells seashells by the seashore, right? Hard to say. Saucer-shaped ships. High in the sky, metallic but no shine. Rather dull gray. They hovered overhead in a V formation. That definitely doesn't sound like the Air Force. This was sighted in Salem, Oregon. So it's got the city and the state. All this data is, of course, US-centric. It's got the timestamp in convenient ISO 8601 format. And so here we've just got it's at like sometime in the afternoon. The date's approximate. So this one happened on September the 15th of 1950. One of the fields in the data set is the shape of a UFO. This is important, I guess. This one is a disk. Some of the shapes are like light or object, which doesn't really feel like a shape to me, but like circles, squares, triangles, right? They've got a duration, which is written in a way for humans to read. So literally the string 15 minutes, or about an hour, or a couple of minutes. It's a human parsable thing. Original link back to the report. The full text of the UFO sighting. These can be quite delightful to read if you just pick a random one and read them. There's some of the best stories. And then a latitude and longitude for the city that the event took place near. And so this is the data. Tim actually no, this isn't that data. The Bigfoot data, he actually annotated it with weather data as well. But for the UFO data, he didn't. The idea with the Bigfoot weather data was this: maybe on a foggy day, there might be a grizzly bear up on its haunches, and and it's foggy, but so you weren't sure, so it's probably Bigfoot, right? So this is the data that we're going to play with. I encourage you to go online and get this data and do your own fun stuff with it. But we're going to do it with, explore probabilistic data structures with it. And so that begs a question. What the heck's a probabilistic data structure? How many people here have heard of probabilistic data structures? That should actually be all of you, because I just mentioned it in the previous slide. A few of you? Who has used them before? I see like 4 hands. Well, you're in the right place. I did a super scientific survey on Twitter a couple of years ago when I was putting this talk together, and 58% had never heard of them. And 22% had heard the term. And I suspect most of them had heard the term in the question. So we're at 80%. 4 out of 5 people didn't know what a probabilistic data structure was. The other 20% were split more or less even between knowing what they were and having actually used them. So if you don't know what a probabilistic data structure is, a probabilistic data structure, what it is, then you're in good company, because 3 years ago, I didn't have 4 years ago, whenever I did this survey, when I was putting this talk together initially, I had no idea what they were either. And they're really cool. But to understand them, I want to look at their evil opposite, the deterministic data structure. These are the data structures that you use all the time. You've used many of these, I'm sure. Maybe you don't even know you've used them, but you've used them. You've got lists and arrays and graphs and stacks and queues and those sorts of things. These are all those data structures that you learned about in computer science. It's like, but why do I need to code a hash table? JavaScript is a hash table for everything. There's hash tables built into my languages already. And at a certain level, there's some practicality to that, but these are the data structures we're using. They're deterministic because when you shove things into them, you get them back. They do a thing that you expect every time consistently. If I shove a bunch of stuff into a list, I know I can get that stuff back out of the list. When I shove a bunch of stuff into a hash table, I know that it will come back out of the hash table. It won't do anything unusual. It's deterministic. And I'm going to look at one of these deterministic data structures in particular. And this might be review for some of you if you took computer science and you took the data structures class. But I'm going to talk a little bit about hash tables and how they work. Is that okay? There's probably some of you that haven't studied this. Not everyone has a computer science degree. I didn't. And so if you haven't taken a data structures class, this is good to know. So a hash table is, well, it's practically everything that we use in computing all the time. I'm guessing the mix here is probably Java and JavaScript developers. If you're a Java developer, hash tables map, hash map specifically. If you are a .NET developer, they call them dictionaries. If you're a Python developer, they call them dictionaries. If you're a Ruby developer, they call them hashes. If you're a JavaScript developer, it's everything that you use in JavaScript. It's all one big hash table. Everything's an object, right? Key value. It's the key value pair thing that you use. This key contains the value, this other key contains the value in this nice little structure. And so here we've got this very complex and advanced diagram of a hash table. It's got city, state, timestamp, shape, summary, values in it. And the reason they're called hash tables is because they make use of hashing functions. And many of you are probably familiar with hashing functions as well. The idea behind a hashing function is you give it some data. It's a deterministic thing. You give it some data. Here, I'm giving it the 6 bytes here. That happens to be the ASCII values and the UTF-8 values for the word Scully, for maximum X-Files UFO themedness, and a seed, a random number that goes into this hashing function. And this hashing function will then take that data, and with that seed will always generate a number. And that number is always going to be the same every time for that seed and for that data. You can give it lots of data, gigs of data, or bytes of data, and it's always going to generate a hash, a number of a fixed size. In a hash table, you're probably using some sort of efficient hash that's not necessarily particularly secure. So lots of people have heard of hashing functions, and they think of it as like SHA-256 or something like that. Those aren't the kinds of hashing functions you would use in a hash table because those are cryptographic. You take a password and you hash it. You don't want a small change to the password to result in a small change in the number you get out, because then it'll let you guess the password. But if you're making a hash table, it doesn't matter. You're not worried about people guessing the keys to the hash table. So you want fast hashing functions, not safe hashing functions. But what a hashing function does is it takes that data and spits out a number. That's really all they do. And it does the same number every time. A hash table then is an array of linked lists where we take the key and we hash it. So we take the key, we're going to add the word Salem to our hash table. And it's going to be in the field city, so city of Salem. So we take the string city, the bytes that make that up, we run it through our hashing function, and we get a number out. We do a modulus of 10 on that. Why 10? Because our array here has 10 elements in it. If we had 100 elements, we'd do a modulus of 100. I'm just using 10 because it fits on the screen. And that will give us a number from 0 to 9, which is an index into that array. And then we say, okay, well, I got a 1. So in position 1, I add an object to my linked list that has the value that I put in, city, and for the key, and then has the value for that key. Then when I go to read it, well, oh, yeah, okay. I thought my pointer wasn't working there for a moment. Same thing here. We're adding another value for state, Oregon. When state through that hashing function, we get a different index. And so it goes to position 4. And when we go to read these out, it's just the opposite pattern. We go ahead and hash the key that we want to read, we get an index, and we get a linked list. And we can go through that linked list. Occasionally, you will get a collision. This is fine. This is why we're using a linked list. So we want to put in the value for shape. And shape, when we do the math here, happens to be an index of 1 as well. And so in this particular hash function I'm talking about, there's more than one way to solve this problem. We're going ahead and adding another element to the linked list. So now index 1 in our array has 2 elements in the linked list. And so when we go to read that, if we go to read city, then we do that same computation backwards, we hit our linked list, and we walk that list until we find city. So this is a basic hash table. And one of the reasons I'm talking about these is not just because they're kind of interesting, because they actually are kind of neat, and they're kind of simple and elegant, but this hashing of your data and moduling them to get indexes is used repeatedly throughout probabilistic data structures. A lot of probabilistic data structures will hash away your data and just store the results of that hashing to determine whether something's in there or not. And so when we are picking our data structures, like our deterministic data structures, sometimes we are looking at their complexity of their operations when we pick them. Do we want an array or do we want a linked list? Well, there's a trade-off there, right? The linked list is very compact. It doesn't have any wasted space, but its time complexity is bad. If I want to find something in a linked list, I have to walk all the way down the list until I find the thing. So it's got a time complexity of O of n. An array, if I want to access things in it, has a time complexity of O of 1. You just go to the thing you want. But the space complexity varies. And so we're making these sort of trade-offs where we're looking at our data structures and we're saying, do we want something that's fast but takes up more space, or do we want something that takes up less space but is fast? There's trade-offs that we're making there. Or less space and is slow. And there's trade-offs we make there. But that's not really the full picture, because a lot of the trade-offs we're making aren't just whether, you know, this data structure is fast but wastes memory, or this data structure is slow and conserves memory. But there's other considerations of capabilities, like in the array versus linked list, versus say a hash table. An array, when you want to go beyond, it's a fixed size, and so when you want to grow it, that's an expensive operation, and sometimes you don't want to have to do that. Linked lists have certain capabilities. They're really fast to add things to, and modify. You don't have to ever resize them, but they're slow to access. And so you're making trade-offs for their capabilities as well as their complexity. And so this is kind of a false dichotomy that I'm presenting here. And it turns out there's another trade-off that you can make other than just time complexity and space complexity. I'm calling this accuracy complexity, even though wouldn't be measured in O of anythings. But it's an accuracy trade-off. You're making a trade-off and saying, I want to save a lot of time. I want it to be really, really fast. I want it to save a lot of space for really large data sets. And I'm willing to sacrifice accuracy. I'm willing to have a data structure that will lie to me. Sometimes. And the initial programmer reaction to this is always like, gasp, horror, right? It's like, no, it must always be perfectly accurate 100% of the time, and my code will always be beautiful and perfect, and everything will be glorious, which is bullshit. Right? It's never going to be perfect. It's never going to be glorious. I've written code long enough to know that I'm always ashamed of my code 3 days later. And so our data structures are kind of the same way. We don't actually always need the accuracy that we want. Let's say you're an online video content producer called Fill in the Blank Tube. I'm sure you've used it. And you need to count how many unique users have watched your video. Once you get past a few thousand, how accurate does that number need to be displayed? Once it's into thousands, millions, if it's had 1 billion unique users watching it, might be a lot of unique users. Does it matter whether it's 1,917,000 or 1,903,000? It doesn't really matter that much. And so if you can keep a set of all the users that have watched that movie to get that count and have it be 98% accurate, it's good enough. This is what probabilistic data structures are and what they're for. This is the problem they solve. You've used these without realizing it. This picture of the Devil's Tower in Wyoming in the Badlands, made famous by Richard Dreyfuss and a pile of mashed potatoes. That's a joke for all the people over 50. It was in Close Encounters of the Third Kind. It's a gorgeous monument. It's a really cool piece of rock that's out there. Oh, this is a JPEG. And you don't know it, but that pixel on the top right, it's the wrong shade of blue. And you know what? It doesn't matter because you still see the picture. This is a lossy compression. It's a little bit lossy, but it's good enough. It solves our problem, gives us the image that we want to see. Some of the details are wrong, but it's right enough. In a way, metaphorically, a JPEG is a probabilistic data structure. So, everyone tracking so far? Am I loud enough? Am I caffeinated enough? That's the question. Getting down to a little more of the details here, a lot of probabilistic data structures can be thought of as sets with limited or unusual properties. And by sets, I mean like the whole Venn diagram set theory thing. And so obviously every probabilistic data structure, you have to be able to add things to the set, because if you can't add things to it, it's not very useful. But some of them can only do things like, well, you can add and get the cardinality, how many things are in the set. Or you can add and test to see if something's in the set, but you can't get the list of the things in the set. And so it's got limits on which capabilities of a set that you can do. Some of them will allow you to union them together, some of them won't. Common things you can do with probabilistic data structures is you could test for membership. So this is the classic example of this is the Bloom filter, which is one we're going to talk about. Is the thing in the set? You know, I've added the star, the square, the circle, and the triangle, and then I can say, is the square in the set? Yes or no? Now you can use a regular set for this as well, but if you have a million things or a billion things, like say usernames, you might want to say, is this username taken or not? Probably. That might be good enough if you have a million users. Also, these shapes I'm using are totally not the symbols on the Redis logo. So membership, that's a common thing to use. Another one you can do is cardinality. This is for counting. I've added things to the set. How many unique things have I added? So you just start piling data into there. Usernames, for example, is a good one. And that would be counting how many users have watched a video, because you can get the cardinality of that set, the number of unique items in that set. And here I'm going to take a little bit of liberty with the idea of a set for my metaphor here, because you can also do frequency, which is going to tell you how many of each thing is in a set. So I have the star has been added 5 times, the square 4 times, the circle 6 times, the triangle 3 times. And so you can create probabilistic data structures that act like sets, but there's a numeric value associated with them, a frequency, a count of how many things are added to that. Related to frequency is a ranking algorithm, a probabilistic data structure that is doing what frequency does without keeping track of the count. And so it says, this is the most common thing I've seen. This is the second most common thing I've seen, the third, the fourth. And it ranks them and gives you like a top 10. This would be great for leaderboards when you have 1 million people playing Fortnite or something like that. Another thing that you can do with these sets is do similarity measurements against sets. We'll talk about this more later. You can compare a probabilistic data structure using similarity, certain probabilistic data structures, to see how similar these two sets are. So like the first set here is got all the shapes, the second one's missing a star, the third one's missing a couple, and there's ways to measure numerically how similar these are. So these are some of the things you can do with probabilistic data structures, some of their behaviors. There's a lot of probabilistic data structures out there to choose from. I've got a small selection here that basically was the result of Googling something. I'm giving away the speaker secrets, ain't I? The ones that are highlighted in blue, if that blue is visible to you all, I hope it is on the projector. Those are the ones we're going to talk about today, time permitting. The ones with the little red dagger symbol on them are available in Redis. The one with the double dagger, the hyperlog log, is available on vanilla open source Redis. The one with the single dagger is available on Redis Stack, which is a developer-friendly version of deployed version of Redis that has a probabilistic data structure extension called Redis Bloom. And so these different data structures, some of them are quite neat. Balloon filters and cuckoo filters are all about checking for membership. You can add things to them. Balloon filters or cuckoo filters, I think cuckoo filters allow you to remove things as well. Balloon filters do not. Hyperlog log is all about counting. Hyperlog log is cool because in 12 kilobytes, you can count the number of unique atoms in the universe. That's kind of impressive. It can keep track of really big counts. I have no idea how it works internally. It's just black magic. Count min sketch is available on Redis. It lets you count frequency of different items, so you can add different things to the set repeatedly, and then you can get a frequency count from them. T-Digest is recently added to a Redis stack, and I haven't looked at it that closely, but it's a time series thing where it will infer values in a series, probabilistically. We're going to look at Heavy Keeper, which is really good for looking at ranking, and it has this capability where values that have been in there for a while but haven't been updated will get eroded, and other ones will float to the top. And so it's really good for like trending topics and like network traffic analysis and stuff like that. Minhash and Simhash were created by Google, and they are used to calculate document similarity. And so you've got a couple different documents, and you want to say, how similar are these documents without having to compare an entire document to an entire document, which is an expensive proposition. So these are some of the ones we're going to look at. I mentioned briefly Redis Stack. Redis Stack is the Redis. How many here have used Redis in the past? Quick show of hands. A lot of you? Okay. Who have used it for something other than a cache? 2 people. 3, yeah. It's always like a tenth of the number of people that used it. So if you've used Redis, Redis Stack is Redis. It's the Redis you know and love, with extra add-ons like that add new data types to Redis and add new methods. So we got Redis JSON, which adds a JSON data type. Search, which lets you search all your hashes in JSON documents. A graph, which lets you store a graph database in a key in Redis, which is pretty cool. Redis time series, which is a time series database. And then the one we're going to look at today in our demo, Redis Bloom, which adds several probabilistic data structures. You can get all these here at this URL, instructions on how to install Redis Stack. I always use Docker. So let's go into a Bloom filter. So Bloom filter is the first one we're going to look at. How are we doing on time? We got about 20 minutes. I still got time. It'll be fine. A Bloom filter is a set that lets you do 2 things. You can add to it, and you can test for membership. It will answer no, this thing is not in the set, or probably this thing is in the set. It doesn't say yes, it says probably. So you can get false positives, but you can't get false negatives. The cool thing with the Bloom filters is when you create it, it is of a fixed size, and it never gets any bigger. And every operation on it is O of 1, and which is pretty cool. The use case I always like to trot out for what you would use a Bloom filter for is username uniqueness. If you want to determine whether a username is unique or not, I'm signing up for Spacebook, which is like Facebook, but for science fiction authors. And I want to see if the username's taken or not. I can't exactly do a select star from users, where username equals the username I want to use, because I could have 10 million users, and that's going to be a very slow query. And so what I can do instead is I can add all of my users to a Bloom filter. And then I can ask the Bloom filter, hey, is this username taken? And it'll say no. Great, I'm going to use it. Or it'll say probably. And then we'll tell the user, oh, we're sorry, that username is taken. Honest. And this works fine. So it just means certain usernames will never be used. But it means that I can have 1 billion users and check for uniqueness of that username and be 98% accurate. It's a pretty good trade-off. The way a Bloom filter works is, well, let's look at the parts of a Bloom filter first. There are 2 parts to a Bloom filter. Down here in the bottom, we've got some hash functions. Remember the hash functions? And their corresponding seeds. It's all the same function, different seeds. You could use different functions too, that would work. But definitely different seeds. And We have picked 3 here, but you could pick more or less depending on what you're doing, and there's a formula for figuring that out. I've used 3 because it fits on my PowerPoint slide. And then up top here, we have a bit array, and that is of a fixed width as well. My implementation in JavaScript for this is very naive and inefficient because you just need bits. You don't need bytes. And so manipulating individual bits in an array, what's the easiest way to do a bit array in JavaScript? An array of booleans. It's the most inefficient way to do it. But you would actually probably want to do this like in C and actually be bit twiddling. But you've got this array. This one is 10 wide, again, because it fits on the screen. And when we go to add something to the Bloom filter, what we do is we take the text of that something, or the data of that something, and we run it through these hashing functions. So we're going to add some UFO sightings that have been reported to our Bloom filter. We want to see if we want to be able to check to see if we've heard this story before. And so this is one of my favorites in the data set. I mean, I haven't read all 112,000 of them, but this one's really funny because it's a story about these guys. It's called Megatron in the Bushes. Everyone seen the Transformers, right? Anyone seen the Transformer cartoon back in the 80s? Again, I'm talking to everyone over 50. So these guys were driving down this highway somewhere in Arizona, and they stop to take care of a necessary bodily function. We've all been there. Had a little bit too much to drink. I need to take care of something. So they go out into the desert, go behind a bush, and as they're heading back there, they hear this strange sound. They hear something that sounds like Megatron transforming from the Transformers. That sound that they would always make in the cartoon. And so they freak out. They get in their car and they head off the highway, and these lights come from over the mountain and chase them for like 50 miles down the road. I'm sure they weren't high at all. Great story. Totally true. Anyhow, we want to know if we've heard the story before. And so what we'll do is we'll take Megatron in the Bushes, and we'll run it through these hashing functions, each one. And running it through those hashing functions, we'll get a different number for each hashing function. So we've got 3 numbers. And this is starting to look like a hash table, isn't it? Because we're going to take those and modulus them by the width of my bit array. And it's going to give me indexes. And then for every place where I have an index, if there's a 0, I flip it to a 1. Now when I go to read from the Bloom filter and say, is Megatron in the Bushes in the Bloom filter, I go out, I do the same computation, I get my same indices, and then I look in the Bloom filter and say, are they all 1s? If they're all 1s, probably, he said with confidence. If they're not, then definitely not in there, because nothing with that data has ever set that position to a 1. If there's a 0, it's a no. If it's all 1s, it's probably. Let's go ahead and add something else. There's another UFO sighting. In the data set, it's actually all in uppercase. It's all in yellow case. I seen a UFO. It was also in bad grammar in the data file. I seen a UFO when I was about 13 years old. This one goes through that same process, but this time when we add things, we get a collision. So before we modified 0, 2, and 6, or 0, 5, and 6. And this time we get 2, 1, and 6, and 6 is the same. And so 6 doesn't change, it just stays a 1, and the other 2 get flipped. And if we try and read I seen a UFO when it's about 13 years old, we get all 1s back. And if we try to read Megatron in the Bushes, we get all 1s back, and everything's happy. The Bloom filter is accurately telling us that this was added and this other thing was added. It's great. And the reason we have multiple hash functions is so that when we get this collision, it doesn't give us a false positive as quickly. It mitigates the damage that a collision do. It does mean that our Bloom filter needs to be wider to accommodate the fact that we're going to set more bits. But when we have a collision, the impact of that collision is lessened. So there's a trade-off there that you're making when you set these up. But what can happen is that as you add things to these Bloom filters, eventually it's going to get pretty full. Eventually it'll get completely full. And then it always lies. Once these are all flipped to 1, everything's probably in the Bloom filter. And so here's an example of a collision. Investigators from the Bigfoot Field Researchers Organization, the BFRO, observed a glowing green-blue sphere. I definitely trust the investigators from the Bigfoot Field Researchers Organization to give accurate UFO reports. When we run this sighting through our structure here, we get indices, and they're all set to 1 already. Now, those were set to 1 by the previous things, but this is going to come back as probably true. But if we had added this first, if we had added it and then asked, well, then it wouldn't be a false positive because we added it. But if we hadn't added it and asked, it would be a false positive. And if we had added it first and then added the other things later, then, well, what's the false positive and what's true, right? This is why they're probabilistic as opposed to deterministic, because that order impacts whether it's a false positive or not. There's always a little bit of doubt and accuracy in them. But, I mean, on the flip side, I've just shoved a bunch of text into 10 bits, and I've asked it meaningful questions. And so you can see how this could be very powerful. I mentioned that you have decisions on how wide you want to make these things and how many hashing functions you want to use. There's some easy math to do that. I'm not a very mathy person. This actually looks intimidating, but it's not. And honestly, there's online calculators that you would be better off using to do this anyhow. But what you do is you have an idea of how many things you want to add to your bloom filters. Like this bloom filter needs to hold 1 million entries. And you take a guess of the number of bits that is needed to do that. And then you use the bottoms function and solve for k. And then you use that k and solve for p using the top function. And then you look at that rate and say, is that acceptable? If it's not, then you change your number of bits. And so this is the formula if you want to do it by hand. The easier way to do this, of course, is to use an online calculator. They're easy to find. Of course, coding up your own hash table is kind of, or your own bloom filter is kind of a pain. Redis has a bloom filter baked into it already. You can create one with the bf reserve command if you are using Redis Stack. You give it a key name that you want to be the container for that bloom filter. You give it an error rate, so this is 99.5% accurate, and you give it a capacity of how many items you want in it. Then it's just a matter of calling add to add things to it, or you can call mad, which is multi-add. I'm mad. Yeah. And then you can, there's an exist function, which will tell you whether something is in the bloom filter. And there's a multi-exist, the mexists. That sounds like Mexican revolutionaries, doesn't it? I like pronouncing all the Redis commands, like set add is sad, the loneliest of all Redis commands. So that's a bloom filter. I'm looking at my time here. I don't think I'm going to do the demo of this, but it's really easy. The commands are there's like 3 commands. Reserve, add, exists. That's all bloom filters do. Let's take a look at min hash. So min hash is used to determine how similar documents are. You could use this for cheating, determining plagiarism, or to determine whether like a page is worthy of being re-indexed. And to do that, you need to turn the documents into sets, and then you need to compare the sets. So how do we compare sets? How do we say how similar are sets? Well, there's a simple formula that you can use called a Jacquard similarity. Some of you may have heard of this. It's not very complicated. All you're really doing is you're taking the cardinality of the intersection, that'd be the 2 bits in the middle, with the cardinality of the union of the 2 sets, and getting the ratio of those. So here, Scalder and Molly, face swapped from the X-Files, have the states in which they have seen probabilistic data structure, or which the states in which they've seen UFOs in the U.S. So Scalder has seen them in California, Nevada, Oregon, Wyoming, New Mexico, and Ohio. Molly has seen them in Florida, Kansas, South Carolina, West by God, Virginia, Take Me Home, Country Road, and New Mexico and Ohio. New Mexico is where Area 51 famously is at. Ohio is where Wright-Patterson Air Force Base and Hangar 18 is famously at. So this seems true to me. And so you just divide those, and you see that these sets are 20% similar. So that's Jacquard similarity. So if we can turn our documents into sets, we could do Jacquard similarity against them. So how do we turn documents into sets? We could just take the words in the documents and make sets with the words, but then they're all going to be similar because they're all in English. And so a way of overcoming that is to break the documents up into trigrams, sets of 3 words that overlap. This is called shingling. I'm rushing a little bit because I've gone a little long. So shingling is where we take a group of 3 and we take the next group and the next group, and they're overlapped like shingles on a roof. And we build a set of these trigrams instead. So this is from Megatron in the Bushes. We notice to our left, further off into the mountains, a bright glow. And we've shingled this and created a set of trigrams. And so now Scalder is making his report for Skinner, and Molly's doing the same. And we can take these trigrams and do the same calculation, and we get a 7 to 11 ratio there. So we get 63.6% similar in these 2 documents. But we're comparing strings. This is inefficient. If you were comparing everybody's essays to everyone else's essays to see who was cheating from whom on a test, the number of connections there gets big fast. And so, well, what can we do about that? Well, we can use a min hash, which is a way of hashing away the data to create a set of numbers, and we can compare the numbers. So to do this, we get a hashing function. Actually, we get a set of hashing functions. That hashing function is run over every item, every trigram in the report. So to create a set of numbers. And we do that, and then we take the minimum number. So right now we notice 2 corresponds to 325. The mountains A at the bottom corresponds to 312. And we just get a bunch of hash values, and we take the smallest one, the minimum one, the min hash, which is why it's called min hash. We do the same with another hashing function and another hashing function, and this gives us a set of numbers that is like a fingerprint for that document. 233, 143, and 102. We can do the same thing for Molly's and get different numbers, and then we can take those sets of numbers and do the Jacquard similarity on those. And this allows us to get a nice compact signature on a document. You'd probably use more than 3 hashing functions. That you can store. Like, I've turned this document into a small set of numbers, and then I can just turn new documents into the same small set of numbers, and now I'm just comparing sets of numbers instead of lots of strings. Way more efficient, way smaller. Pretty cool, right? We'll skip that slide. I've got about 5 minutes. I'm going to try and go through Top K here. How much time do I got? About 5 minutes? Would anyone be terribly offended if I went over by like 3 minutes? You want me to keep going, or you want me to cut it short? I would love to buy everyone a beer from Redis, but I know I'd get fired if I did that. But I'll buy you a beer. Yeah. Will I buy you a beer? Well, is your name in the Bloom filter or not? Yeah. Probably. Yeah. So let's look at Top K. Top K is a way of ranking items. It's actually 2 data structures combined together. There's a min heap and a heavy keeper. The min heap is a heap. I'm not going to go into how the heap works, but the heavy keeper is the thing that will count, and it counts in an erosive way. What do I mean by that? It means that as you add things to it, occasionally you get collisions, and then things that have been added to it, their count will be decremented. Let's look at a heavy keeper really quick. This is a little complicated, but accessible. A heavy keeper's got 2 main parts. It's got a set of hashing functions. You start to see a pattern here, right? And it's got several arrays of buckets. And the bucket has in it a place for a hash value, a number, and a count. So it's a bucket with 2 integers in it. And what we're going to do, well, let's look at a new one. A new one is just zeros everywhere, nulls and zeros. Hash count's not defined, the count is 0. It's just 0 and 0. When we go to add something to a heavy keeper, let's add the word object. It again goes through this hashing and modulusing operation to get an index. So this time I got %w here, presumably it's wide, but I've only got room for like 3 on the screen. And so we get indices for the word object, and we look in those indices. So here we've got 2, 1, and 2. So we look in position 2, position 1, position 2, and we say, is there anything there? Is there a hash value? Is there a count? If the count's 0, there's nothing there, so we take it. And so we take our hash value and shove it in there. Right, I wish I could point. My pointer isn't working as well as I'd like it to. But we take our hash value and shove it there into that particular index, and we increment the count by 1. If we add the word object to the heavy keeper again, then it computes the same values, gets the same indices. It looks in there and says, the hash value in this bucket is the same as the hash value I just computed. It's in this index, so let's just increment the count. So now they're all set to 2. When we go to query it, we just reverse this process, get the numbers, and we take the biggest number. So right now, if we say, how many times is the word object added to the heavy keeper? It'll say 2, because all of them report 2. It just takes the biggest, which would be any of them. Let's add a different value. Let's add the word light to the heavy keeper. Well, we do the math, and the first 2 rows, we get different indices, and there's an unclaimed bucket, and so we just put our values in there. But in the third one, we have a collision, and the bucket is occupied. We go there, and we see that the hash function, or the hash value in that bucket is different than the hash value I just computed, so what happens? Well, there's a chance that that 2 is going to get decremented to a 1. And if this happens enough, it'll get decremented to nothing. And that probability is computed by taking the magic number b, which is slightly more than 1, but just is like 1.05 here, to the power of negative whatever the count value is. And so this, for big numbers, is going to give you a really, really small number. If there's 10,000 things in there, this is going to compute out to an unlikely event. But if there's 2 things in there, it computes out to 90.7%. And so what tends to happen with heavy keepers is that the more that gets pushed into there, the more likely it is to not be eroded. And so it keeps the heavy things, hence the name. And so we've got 90.7%. It's probably going to be eroded. So let's go ahead and erode it. And now we have we've decremented that by 1. And when we go and try and read what's the count of light, we get 1, 1, and not there. 1's the biggest, so light was added 1 time. When we add object, we go to read the value of object, we get 2, 2, and 1. 2 is the biggest, and so we report a count of 2. And so this allows us to count things. You can see how things would erode over time. It's like, well, this thing got really big, but we haven't seen it in a week, and it's slowly whittled away by collisions over time. It's like eroding a canyon. Whenever we add things to the heavy keeper for top K, we also add them to the min heap and say, is this bigger than the thing that's at the bottom of the heap? If it is, then we swap them out and it recalculates. And then we want to get like the ranks of things. So like, give me the top 5 items like the top 5 most commonly used UFO shapes. Then we just read the min heap, because that's a lot faster than interrogating the heavy keeper. And so together these create a top K structure. It also creates a counting structure, which almost always gives you numbers that are lesser than what they should be. To use top K in Redis, you call top K reserve, give it a key name for the key, give it a number of items you want to keep track of, like say 3, give it a width for how many buckets you have, you get a depth for how many hashes you have, and you give it a decay rate, which is that number that's slightly almost 1. It's the reciprocal of that number. So this is 0.9. And then we can add things using topk.add. We can query things using topk.query. That will say, is it in the top K, yes or no? We can get the count of a key, of a value, and it will go to the heavy keeper and get the count out of it. And we can get a list of the top K items. And so I've got a demo, but I'm already, I'm right at time. Let's do the demo really quick, and then you can just give me a big round of applause. Does that sound good? Okay, because the demo's fun. I'm not going to go too much into how the code works, but the basic idea of it is I've got this big data file of probabilistic data structures, or I did it again, of UFO sightings. It's right here. It's a big CSV file. It's got like 112,000 lines in it, roughly, and it's just this giant CSV file. And what I've done is I've got 2 little Python programs here. One is called app.py. It's a little Flask app that just hits Redis repeatedly to get the count from the top K structure. And build.py uses Pandas and Natural Language Toolkit to process all the UFO sightings that are in there, find the words in them, and add them to the top K structure in a big loop. So let's run this thing. And then I got a little JavaScript application that lets you see these things. So let's go ahead here. We'll start the app. So it's reading the probabilistic data structure right now, and I have one from an earlier run there. And let's run build. So build is going to read that CSV file. It takes it a moment to start spinning, and now it's just going through the sightings and sending all these words here. This is very slow because I'm putting it in console. If I was doing this against Redis and not logging it, it would be much, much faster. And if we go to here, I've got a little GUI that is now counting the top words used in UFO sightings. Object is number one. Oh, no, it's not. Lights is, and light, and top shapes. And these, as these accumulate, they'll rearrange, and because it's probabilistic. You can actually go into Redis here as well, and you can see I've got these two data structures, and I can do like a, let's do a top K dot list UFO words, and whoops. Oh yeah, hit it again. There we go. So then it spits out the top K. And if I want to get the counts, I can do with count. So, and you see they're in order. So, pretty neat. I'm biased because I wrote it. but yeah, so let's just leave that running in the background. I'm sure that'll be fine. It won't drain my battery in 2 minutes. So that's my little demo. I've got a slide full of links here. You can go check out. All these slides are out in the GitHub repo, so you don't need to worry about capturing these links. What you need to worry about is the QR code at the end. I work for Redis. Go check out our stuff. We got a Discord server at discord.gg.redis. We got free classes at university.redis.com. You can sign up for all this stuff and do it in the cloud for redis.com/tryfree. If you use code STACK200, my boss will know you saw my talk. And here's the link you actually care about. Thank you very much. The big problem is I have like 65 minutes of content.